Hey, mathletes. In this video, we're going to talk about concavity and points of inflection. And essentially at this point, this is the final thing that we need to draw a nice graph without a graphing calculator. So after that, we're going to put it all together and we'll do curve sketching, putting everything together. But we'll talk a lot about the other parts in this lesson as well. So first, what I want to look at is this graph of x, f at x. So what we've talked about in the past is where are we increasing, where are we decreasing, where are we neither increasing or decreasing. We've got a relative max, we've got a relative min. So what we're going to talk about in this one is concavity. So I always think of concavity as I'm holding my milk spoon, and either I'm concave up and I'm catching my milk, or I'm concave down and I'm not catching my milk, right? Same idea here. Look at this nice polynomial I've got for us. So I can tell over here from negative infinity, I'm concave down. I reach my relative max. I'm still decreasing. I'm concave down until right about there at that number C. On the other side of that value C, I turn to concave up. So, I mean, visually I can tell where I'm concave down and concave up. But what if we don't have the visual? We'll go back to this idea of the tangent lines that we use to discover if we were increasing or decreasing. So if I'm concave down, what do you notice? If I'm concave down, I'm underneath all of those tangent lines. And if I'm concave up, I'm above all of my tangent lines. All right. Okay, so the same idea as we did for increasing and decreasing. Okay, so let's put that into some facts here. So for a graph f at x, I'm concave down if f at x lies below the tangents on the interval. In the above example, I'm concave down on the interval negative infinity to C. I'm concave up if I lie above my tangents. And in the above example, that would be C to infinity. And notice I didn't include C in either of those. When x is C, this is called our point of inflection, where we're changing from concave up to concave down or vice versa. Okay, so what are we going to do here? For a graph that is twice differentiable, y is equal to f at x, we're going to be concave up when the second derivative is greater than 0. Therefore, if we're concave up, well, think, then we should have a relative min on that interval. And if I'm concave down, that means our second derivative is less than 0, and we should have a relative max on that interval somewhere. And to find a possible point of inflection, well, guess what? It looks a lot like the first derivative test. We're going to find out where the second derivative is equal to 0 or where the second derivative does not exist. Now, we don't call these critical numbers. That's used for the first derivative test. So I've heard all sorts of names for it over my many years of doing this. Important numbers, whatever you want to call it, okay? Just technically, we shouldn't call it a critical number. So to put this kind of in summary again, if the first derivative is positive, then we're increasing. If the second derivative is negative, we're decreasing. If the second or the first derivative is 0, then we have a possible relative max or min. Remember, it's not guaranteed. If f double prime is positive, then we're concave up. If f double prime is negative, then we're concave down. And f double prime is 0, then we have a possible point of inflection. Okay, try to keep that in mind because in the next lesson, we're going to look at putting this all together and it starts to get a little confusing. There's so much a curve sketching question that you need so much information. Okay, let's try just one. Determine the relative extrema, concavity, and any points of inflection for the following function. All right, so any relative extrema. So to find my extrema, the first thing I'm going to do is I'm going to take the derivative. 3x squared minus 3. And since it's asking about concavity, I need the second derivative. So I might as well do that right now. All right, there's my derivatives. And sometimes that can take the longest amount of time. Okay, here we go. To find our relative extrema, what I need to then find is my intervals of increase and decrease. And what I like to do when I'm doing these, friends, is I like to write this out because it helps keep my own work organized when I'm going through these things. Okay, when do we get an increase or decrease? Well, remember, it's when the first derivative is equal to 0 or when the first derivative does not exist. Well, our first derivative is a polynomial, so it always exists, so nothing to worry about there. So what we do is we set this thing equal to 0 and we start solving. So what we're going to get here is x squared, add 3, divide by 3 is 1, square root that. So remember, I get a positive and a negative 1. So there's my critical numbers. Okay, and I box it to keep my work straight. Now what I'm going to do with my critical numbers is I'm going to find those intervals of increase and decrease. So -1, +1, and we do test points. So I always like to do a number pretty far away, -100, 0, and 100. And recall what we do with those test points. We sub them back into the derivative, okay? And our derivative was equal to this, right? Or I've got it boxed up here for that exact reason. Okay, so when I stick in -100, I'm going to get always going to be positive because it's being squared. So 300 minus 3, whatever, it's positive. When I sub in 0, I get a negative. And when I sub in positive, I get 100. So what does that tell me? It tells me that right here, when x is equal to -1, I go from increasing to decreasing. We have a relative, or at least something going on, maybe our absolute. We have a relative maximum. I should write that above, a relative maximum, because we go from increasing to decreasing. We have a relative minimum, or maximum, sorry, at f is -1. Then at +1, we go from decreasing to increasing. So when x is equal to +1, we have a relative minimum at f is 1. And we could find those values by subbing them back into the original function right here. Okay, now let's move on to concavity. So concavity. Again, concavity, our new thing for today, is where the second derivative is equal to 0 or it does not exist. Well, again, it's a polynomial, so it exists everywhere. So I only have to worry about where that second derivative is equal to 0. Well, that's an easy one. Sometimes it can be difficult when we're looking at a rational function. And essentially, I repeat the process I did with the first derivative. So I take a critical number, or I take a number to the left of this significant value of 0. So again, I just like to be ridiculous and go -100 and +100. And now I sub that back into my second derivative. Well, I mean, it's easy to see. It's negative and then positive. So what does that tell me? Well, it tells me that on this interval, I'm concave down from -infinity to 0. And on our other interval, we're concave up from 0 to infinity. All right. Well, look at what we know here, friends. We know quite a bit. We know our intervals of increase and decrease. We know where our maxes and mins are. And we know where we're concave up and concave down. Well, didn't ask us to draw it, but let's take a quick shot at drawing this thing, which we're going to do in our final lesson. Okay, what do we know? We don't have any asymptotes, but if I go back and look at the original function, right off the bat, what I can tell is I can tell our y-intercept is at 1, okay? Our leading coefficient's positive, and we're cubic. I know all sorts of stuff already. So I know our y-intercept's at 1. I know this thing has a leading coefficient that's positive, so I know this thing has to end going up. It's degree 3, it's odd, so it has to start the opposite way, so it's negative down there. Now what I do is I check. Let's see if our information that we determined here matches. Okay, we've got a relative max at -1, and let's go and actually find what that is. So when x is -1, if we sub that in here, we would get -1 plus 3 plus 1. So that sounds like 3 to me. And if we subbed in x is 1, we would get +1 minus 3 plus 1. That sounds like -1 to me. Okay, so at -1, we have a value of 3. Oops, I had to put that there. Dummy. Try that again. Okay. And we've got a min at +1 down here at -1, which is, let's call it right about here. Okay. And then increasing and decreasing. Well, it tells us we're increasing from -infinity to -1. Well, that makes sense looking at what my partial graph looks like over here. And on that region, I'm told that I'm concave down. So I'm going to draw this. It's going to come up. It's going to be concave down. There's our relative max. I'm still concave down to right there. But then we switch concavity at 0. So we have our point of inflection. I check in my sign analysis. I'm decreasing. Perfect. And it says I decrease to 1. Love it. I'm concave up on 0 to infinity. And there it is. Look at that, friends. That is almost precisely what that graph looks like. The only thing we're missing are our x-intercepts. Guess what? We know how to find x-intercepts. So we're almost there, friends. We're almost at the point where we can curve sketch an entire graph by hand without using a graphing calculator. How cool is that? So again, for today, concavity, we find the second derivative, we set it equal to 0, or we find where it doesn't exist, and that's going to help us find our regions where we're concave up, concave down. Pretty cool stuff. I'll see you another time.